So the next speaker is Davide Barbarossa. This is the last talk of the session, and he will speak about tropical geometry of probabilistic programming languages. But probably we have to wait to have the slides on the main screen.
We can wait. Is this fine? Everyone can hear me and can see good? Perfect. Okay. Well, hello everyone. I'm Davide Barbarossa. This is a joint work that I did with Paolo Pistone, which is sitting somewhere over there. So the two keywords are, as you can see, probabilistic programming languages, of course, and tropical geometry. Let me start by the first one. Let's start by probabilistic, graphical models. Okay, so for example, here is one. So we have a certain number of random variables, those nodes. Maybe those two here are observable ones, and then we may be interested in all the possible trajectories that lead to these observable variables. We can ask typical basic statistical inference questions, like, for example, what's the probability of reaching a fixed outcome, or for a given observable, what are the trajectories which have maximal probability that reach that outcome. Now, on the side of programming languages, we can of course also specify models via programs, of course. For example, let's take this program here. So you can see there are some booleans, there are some lambdas, so this is based on the Lambda-Calculus, so we consider a high-order functional language. And this plus with the subscript is the only probabilistic feature of the language. It's a very simple one. It's just a biased coin tossing. So it goes left with probability x and goes right with probability, the complementary of x, 1 minus x. If you would execute this language in for example, in a call by name reduction strategy, you would see that, well, you have to perform n coin flippings, and if you record all the possible branchings that you can take, you would end up with a model which looks like this, like the previous one. I'm using this x bar in order to indicate the complementary of x. And here, of course, the interesting part is that the typical questions that we could ask before on graphical models now become questions about the computational behavior of our program. So, for example, we can ask what's the probability that the program computes true? Or, given that the program has computed true, what are the reductions which have highest probability? These kind of simple questions. Now, okay, you don't need to understand exactly this program, it's just to show it to you. But if you consider this M, what's interesting here is that since we can exploit all the expressiveness of the language. Here we have a fixed point, so there is some recursion going on, and this would correspond to a model which starts by an initial distribution D, then updates it, then makes an observation on it, and depending on the outcome, it may continue or return. And you see that this is in general, it's an infinitary model. This is just a finite portion of it. What's interesting here is that, of course, usually, finite models are the ones which are maybe most studied, or at least are most simple, while from the point of view of programs, we immediately have a very large complexity, even in very simple cases like the one that we consider. Great. So now for the second one, for tropical geometry. Let me introduce this with a similar example to the previous one. So again, we flip n times a coin, and then we always return true. Well, of course, the probability of returning true is 1, but how can we compute it? Well, we can take all the possible reductions of this program, and maybe here it's a good moment to remark that when I consider these biases of the coins, so here it's, for example, a probability x1, well, actually, I don't want to look at it as a number, as a probability, but I want to look at it as a formal parameter, okay? So here, for example, you see I'm using x bar now. This is, again, a formal parameter, and the act of actual instantiating this with actual numbers, probabilities, will come after if needed. So if I take all the possible branches, this would give, well, a product of all these probabilities, so now it will give just a monomial, and I sum all of them up. If you think about it, this is the same as this big product here. And that's great. But now let me consider another question, like what is the maximal probability? So I want to compute this maximum. And let me make this trick. I apply a minus log in front of everything. Now minus log is a strictly decreasing function. So it goes inside and changes max into mean. And now I have this, I have the minus log of a product, of a monomial, and this is the sum of the minus log. So I have these new variables z, which are the minus log of the x. And okay, this is easily seen to be this. And what's interesting here is that if you look at these two pink expressions, so they look different, but if I actually read the top one and I read, instead of multiplication, I read plus, and instead of plus, I read minimum, then the two expressions become the same one. Okay, and this passage is precisely what's the idea behind tropicalization. It's precisely moving from, for example, the 0-1 interval of probabilities with sum and multiplication as operations to, well, its minus log version, which in this case is the non-negative real numbers. With operations which are now minimum and plus, and this becomes a semiring, and it's what it's called the. I mean, it was one of the possible choices for a tropical semiring. Okay, so I mean, you see that this idea of tropical numbers is related with optimization problems in general, but why it's interesting, it's relevant for any kind of statistical inference. Let me illustrate this again with another example. So consider these two different formal polynomials. And now let us tropicalize them. So I read plus, when I read plus, I read minimum, and when I read product, I read plus. I'm consciously neglecting the coefficients here, the 4, the 6, and the 4. Now I have these two expressions, and if I imagine of now actually instantiating these parameters, x and x bar, with actual tropical numbers, so non-negative real numbers, well, you can easily convince yourself that now these two expressions evaluate to exactly the same thing, okay? And this is why we introduce this notion of tropicalization, which takes a formal polynomial, or in general a formal power series, which is just a formal polynomial with potentially an infinite number of monomials, and evaluates it tropically, so on tropical numbers, and considers it as an actual function. And the point here is that when we make this tropicalization operation, you see that we need to compute a minimum, but we don't need to explore all the possible monomials that are there in order to compute the minimum. We maybe just a small subset of them, it's enough. For example, this polynomial up here corresponds to all the reductions of this program at the bottom to true, and the fact that that this minimum actually shrinks to the minimum only on two monomials corresponds to the fact that the maximum probabilities of this program returning true are achieved by either going always left, so always taking heads, or going 3 times right, or 4 times. It's four calls. Okay, now there is another very elegant way of telling the same story, which is really at the heart of tropical geometry, which is obtained by considering this Newton polytope. So if we consider a polynomial S here, so it's a sum of monomials, let's forget again about the coefficients, but if I only look at the exponents of each monomial, then those are, integer coordinates in a n-dimensional Euclidean space. So we have all these points, and we can take the convex hull of all of them, and we get a solid, or in general what's called a polytope, and this is what's called the Newton polytope of the polynomial, and maybe it looks something like that. And actually, we are interested in the vertices of this object. So the vertices are, of course, this point here. Now, the reason why we are interested in the vertices, we can see it from this example. So if I have this polynomial here, if I expand it, it's this big sum. Now, if I consider for each monomial the corresponding point, I have these 6 points, which are the points here. And if I take the convex hull, of course, I get the 2 simplex in gray. But you see that actually the vertices of that, it's not all the 6 points, it's just the 3 vertices of the triangle, right? So those are the vertices, and if I write it as a polynomial, it would correspond to this much smaller polynomial here. And this precisely corresponds to the idea that I mentioned before about of shrinking the number of monomials to consider when we have to compute a minimum, to shrink it down to a smaller set. Well, actually, for our purposes, we needed to introduce a minimal version of this Newton polytope. It's not really important for the purpose of this talk, but just to give the idea, instead of taking all the vertices, we just take the minimal vertices, where minimal is with respect to the pointwise order on the coordinates. And for example, this is an example here. If we consider this polynomial, then the Newton polytope would be this pink, purple, maybe triangle. But you see that this vertex here at the top right is not minimal. So when we consider the minimal Newton polytope, we kill also this point, and so we shrink even more the number of points that we are considering, which correspond to the monomials. Great. So now, all these things, of course, are very well known, and we didn't, invent all of those. And in fact, there are already previous works that choose tropical geometry based on these ideas, and of course, developing on that for statistical inference typically on Bayesian networks or finite graphical models. So here there is a reference. And the reason is that this Newton polytope can be computed efficiently from the starting polynomial. And to consider this Newton polytope, it's interesting because the vertices of it, as I already said, reduce the space of possible solutions to some optimization problem. And this optimization problem may be things like computing the most likely explanation to some probabilistic model. Now, but this is typically on Bayesian networks and on this kind of models. So our question in our paper was, can we import from all this tropical geometry studies, can we import some of these tools in the world of programming language theory in order to design some programming language oriented methods that would at least express these questions and directly on the programming language, because in this case, there is no substantial distinction between a program which has a finitary behavior or an infinitary behavior, in the sense that we have, that's the whole point of programming language theory, to have a toolbox of tools which work compositionally on the whole program. And in this case, we take high order functional languages, and so we have a lot of theory in that direction. So the 2 points that we want to address is, can we define with these compositional tools the Newton polytope, or actually the minimal Newton polytope for a program, and can we estimate it, can we compute it, or maybe not? So first of the 2 questions, when we think of compositional tools, well, typically we think of categorical or denotational semantics, and there is a very well known, very well studied model of these kind of languages that we consider. So Lambda-Calculus extended with even just one very simple probabilistic feature, just a coin flip, parametric here. And so there are a lot of studies in the denotational models of these kind of languages. And the one which is related with what we do, we really use its properties, is this, which is called weighted relational model. So just the idea is to interpret a type as a set of formal elements, of indices or variables, and a term can be seen as can be interpreted as with something which can be seen as a formal power series, or actually a family of formal power series. And the coefficients are chosen in some fixed semiring. Now, by choosing in a clever way the semiring of coefficients, we can have indeed a model for the language that we consider. And in order to do this, we need to consider as coefficients formal power series themselves, where the variables are the parameters of the program, which means the biases of the coins that we use in our language. Actually, it is already like complex enough to look at closed terms of type bool, and in this case, the interpretation would just give two formal power series, one corresponding to the output true and one to the output false. And those basically collect all the possible reductions to the corresponding output and collect them all together as each of them as a monomial. For example, let's see this very simple case here. We make 4 coin flips as before. And if you would compute the denotation of this program compositionally, then this would give this polynomial here, which precisely corresponds to all the possible branchings in the reduction of the program. You see, we have to make 4 times a choice between going left or right. But again, these tools are well defined for any kind of program, even for programs which have an infinitary behavior. For example, here we have a fixed point, so it's a recursion which is there, and this program corresponds to the experiment of flipping a coin until we find a heads, for example. In that case, we return true. And so we can compute the denotation of this program, and this would give this power series. Now you see that it's an infinite series, and this precisely corresponds to all the possible reductions of this program to true, and you can see it because maybe we find heads at the first iteration, so we only have to go right, so x bar, or maybe we find it at the second one, so we have to go 1 time left and then right, or 2 times left and 1 right, and so on. So now, with this in mind, we can start to think about basically what's the basic idea behind our paper, which makes everything work in a sense, which is this finitary claim about closed terms of type bool, and it says that for each of those there is a finite set, and this is a set of reductions, okay, and this finite set is such that for all assignment of probabilities to the parameters, in that finite set, we can always find a most likely reduction. Okay, so it shrinks it gives a finite set of possible reductions to consider in order to find the most likely one. Or equivalently, there is a number which is an upper bound on the choices on the probabilistic choices that we have to make before finding such a likely reduction, most likely reduction. Now we can make this more rigorous, and actually this follows from this theorem here that we proved on formal power series. If their coefficients are on a discrete set, then when we tropicalize them, so when we consider them as actual functions on tropical numbers, then every formal power series, when tropicalized, coincides to a polynomial, okay? So there is a polynomial which makes this infinitary object, like a formal power series, collapse to a finitary one, like a polynomial. And with this, we can define a number associated with a program, which we call the tropical degree, and this is just the smallest degree of one such polynomial, which makes the power series associated to the interpretation of the program, as I defined before, collapse to a polynomial. Or equivalently, we can take the Newton polytope associated to this polynomial, and this I think that is very nice. We can associate this geometric figure to a program with this idea of minimal Newton polytope actually. Now there is a drawback here, which is that actually the problem of knowing if the tropical degree of a given program is a given number, this is an undecidable problem. So we have to cope with this. Anyway, so this checks the first point, because at least we can define it in terms purely program theoretic and compositional. Now for the second question, well, we know that this Newton polytope is not constructible right in a constructive sense because it's undecidable, but maybe we can develop some framework in which at least it makes sense to estimate it in some way. And this framework, we find it in what are called non-idempotent intersection types. Those also are very well studied in the literature on Lambda-Calculus and this kind of languages. And so the idea is that now we have judgments like this, and we want to build derivation trees. And a judgment consists in having, in the context, a certain number of resources which limit the usage that the program can do to the inputs, and then we have a fixed output for the program. And in our case, we label every of those judgments with this small s, which is a polynomial, again in the variables which are the parameters of the language. And the idea is that each monomial of this polynomial here records a reduction of the program, which has been explored in the derivation that we are building. And here there is a trade-off to take care of, because, well, on the one hand, of course, we want to make this polynomial as small as possible, because we want this to be, at least in principle, feasible. But also we want to, at least we hope to be able to find inside this polynomial, which is generated by this typing derivation, we want to find a most likely reduction inside. So we need to explore enough reductions, right? So there is this trade-off. And the way that we do this is by comparing different reductions at the same time. So the typing judgments actually contain multiple derivations at the same time, and they are a bit complex, so I'm not showing to you the full system. If you want, I can discuss it in the questions. But I just want to show quickly the application case. So this is how it would look like in the usual intersection type case. So in our case, we have multiple of those in parallel. This is just one of them. And for us, we also have to label with polynomials. So here we go. So remember, here as 0 is the reductions. You can think this really as the set of reductions that we have explored in this derivation for n. Here is a set of reductions that we have explored for n1, and so on. And when we apply the calling program to its argument, we need to take care of all the possible concatenations of these reductions, basically. And this actually corresponds to taking the product of the polynomials here. But there is a problem already that you can see, because when the number of application grows, well, this multiplication of polynomials can become easily intractable. So we need to to keep this small as well. And we do this by relying on the literature in tropical geometry, with which we were able to show that there is an algorithm for computing multiplication, which we call Viterbi-Newton multiplication, which takes a finite number of polynomials, and it gives not really the product of all of them, but just the minimal polynomial of the product. Minimal in the same sense of the minimal Newton polytope that I showed you before. And this is now feasible, and this is precisely what we use in each instance of each rule of the derivation in the typing system. So you see that every time that we need to compute products, this will appear also in many other rules, not just the application one. And here we call this optimized products. That's great. Okay, here is an example. I mean, you don't need to understand it again. It's just to show a very simple derivation. And so this is showing that for this program, so we make 3 coin flips and then we return true for the only possible output in this case, which is true. This derivation has explored this set of 2 reductions. Either we go 3 times left, either 3 times right, and you see that it did it by precisely using this Viterbi-Newton multiplication, because at a certain point we needed to compute this product, but instead of computing all the, well, in this case just 4 monomials, we just kept the minimal ones. So that's great. This system, we showed that it is sound with respect to the weighted relational model that I mentioned you before, and it's also complete in a specific restricted sense. But that's precisely it's good. That's precisely what we want, what we expect from these kind of typing systems. And it's also, we could show that it's also complete for the problem of finding the minimal Newton polytope. So for every closed program of type bool, there exists a derivation in our system that generates the polynomial corresponding to the minimal Newton polytope of the program, and therefore also that gives us the tropical degree. So that's great. We are happy, because if we have this derivation, then we can also solve the basic inference task problems. For example, we can trace back the associated maximum maximal reductions from the minimal Newton polytope, or for each given vertex of this geometric figure, the vertex corresponds to a reduction of the program, and by standard tools from linear optimization, we can find an assignment of probabilities to the parameters that make that particular reduction the most likely explanation, for example. Okay, so we are happy, but of course there's a problem here, which is that the problem already of finding the tropical degree is undecidable, right? So we cannot construct this. But that's not the end of the story, even if it's very quickly the end of my talk. It's not the end of the story, because still the fact that we could design these tools, which again are compositional, now perfectly like in the line with the research in programming language theory, allows us to, at least in principle, design a proof search strategy, proof search on these typing derivations, which of course will be complete in the sense that it finds the correct polynomial, but we don't know, we cannot check when it happens. So from the outside of the system, the user has to decide when to stop. And this is the most important perspective that we have to actually implement this and to study the efficiency of this in practice. And then there are also some other possible other perspectives that I leave here for you to read. Thank you.
So maybe time for just one quick question or remark. So I have just one. At a certain point, you have said that you are computing, when you move to the tropical interpretation, you are computing the most likely reduction sequence for getting a result. Do you have an idea if this can be characterized by a strategy, an operational strategy, which is independent from the term, but just?
I don't know. I mean, in that case, the fact of I don't know. I should think about this, but I mean, in that case, the point of finding the reduction with highest probability really comes from the fact of considering this minimum, right, of moving to the tropical one. So it's a completely different, like disjoint reason why this happens than like a reduction strategy reason. So I don't know, but that's yeah, that could be. I don't know.
So thank you. So I think so we can thanks the speaker again,
Thank you.
and this is the last.